Hello students, in today's video we are going to talk about phase equilibrium. We look at the arrangement of the particles of solid, liquid and gas. You can see this in solid they are very orderly arranged, and liquid less order, and in gases it's very random. Okay, so in gas particles they have a very freedom compared to those liquid and solid. But liquid particles, although they are not random as gas particles, these liquid particles they can move, right? They are in a constant motion. And if we think about the collision rate, if you look at this inter particle distance in liquid, it's higher. Distance is less compared to gas, right? That means in liquid there is a huge probability for the particles to collide, right? Here we are focusing on liquid vapor equilibrium. So liquid is converted to vapor, right? So actually if we think about a container in room temperature, let me draw container, right? We have so many water particles. So these water particles, they are in constant motion. Each particle is having different velocities, so they are having different kinetic energies, right? So the particles, let's say, having a higher energy, when they are in constant motion, when they come across the surface of this water contained, that is in this surface in between the atmosphere and the water, when they come across the surface they can escape, right? So they will be actually escape to the atmosphere. So that process is called evaporation, right? If we further consider, if we think about the particle which is inside this container, they are having lots of attractions from adjacent molecules, right? But when it goes to the surface, there is less attraction, there is a tendency for them to move apart. So it's the particles having higher energy, they are escaped. Now what happens to this system? This system, their average kinetic energy is now becoming less, right? Because the particles having higher kinetic energy have been lost to the system, right? It's actually similar to what happens when we sweat. When the sweat in our skin, they evaporate, we say that they absorb the heat from our skin surface, right? That is, they're getting that energy, so the system becomes cold now, right? And now if we focus on this curve, you can see it's actually the curve of fraction of molecules versus the kinetic energy. So you can see here in this there are two curves. One is at T is equal to 300 Kelvin and the other one is 500. If you look at the 300 Kelvin curve, we can see this yellow area that is having the energy, the molecules, fraction of molecules having higher kinetic energy than the energy required for the evaporation process. But what happens when we increase the temperature? You can see there is an increase in the fraction also. This curve is becoming flattened, so there is an increase in the fraction. That means here now both this red region and the yellow region together accounts for this fraction of molecules having higher kinetic energy than the evaporation, right? So, and also I'm actually again stressing that evaporation takes place only from the molecules which are from this very closer to the surface, right? From the surface molecules, not from the molecules inside this, right? So they have to be very clear on that, because the molecules which can evaporate from which are in the inside, that is called boiling. There we observe bubbling also. In evaporation actually we don't see any bubbling, right? So that difference you should be able to keep in mind. Okay, so here we are considering an open system. That is, it's like you are keeping a beaker of water in the table, right? And you are observing actually what happens. Evaporation occurs. So the molecules which are having a higher energy, they will escape from the surface, and they don't have any tendency to come back to this liquid or to this container, right? Because it's actually an open container, so they will diffuse away from this container. Okay, now we are considering a closed system. You can see here initially we have only water, right, liquid phase, and at the beginning there's no vapor phase, vapor in this empty space. So initially for a few molecules they get or they start to evaporate, and they have no tendency to return back to this liquid, right? But with time, when this empty space getting crowded, what happens? The density is becoming higher. So at one particular time, what will happen? They will start to condense and they will move back to this liquid state. So there will be evaporation, at the same time there will be condensation. So after this what happens at a certain stage, the rate of this evaporation and the rate of the condensation will become equal. So we say they attain an equilibrium state, right? At that time there is no change in the macroscopic level of the system. For example, the volume, the pressure, the temperature, the density, everything is same for these two phases. Now as the rate of escaping and re-entering both are same, now the system is in equilibrium. We call it as dynamic equilibrium because the process is still occurring. That means there is evaporation process occurring and there is condensation, both in same rate. So this graph also depicts that. So you can see initially that rate of evaporation remains unchanged from the beginning, but if you think about the rate of condensation, initially it's 0. With time it is gradually increasing, and then we have this state where the dynamic equilibrium starts. So from this line we can say they are in dynamic equilibrium. The rate of evaporation and rate of condensation is equal. So actually all these things we can apply only for the closed system, because if it is an open system we don't attain an equilibrium at all. Okay, so this pressure which is exerted by the vapor in the dynamic equilibrium with the liquid is called as the equilibrium vapor pressure, or it's also called as saturated vapor pressure. That means we have this system, right? Let me draw a closed system, right? So now it is in dynamic equilibrium where rate of evaporation and rate of condensation is equal. So here we are having a pressure inside. So this pressure is referred to this equilibrium vapor pressure, and also sometimes in some books they call it as saturated vapor pressure, because we say now it is saturated, right? That means this empty space is now saturated. Okay. So now let's see what are the factors that affect the magnitude of this vapor pressure. Right, we say the strength of the forces holding the molecules together, that means in other words the intermolecular forces, and then temperature. So how actually? Can you think for a while? Can you pause the video and think? Okay, so let's think, visualize what's actually they are referring as the intermolecular phase. So for example, if we think about maybe a very simple molecule like methane, right? CH4, let's assume we have CH4 liquid here, and it's actually assumption, right? And if you think about the CH4, you know, they don't have any other dipole forces. They only have the van der Waals force, right? The London force. But if we think about water, so I'm in the same condition, same temperature, same atmospheric condition, right? So I'm taking the same amount of water, right? So if we take the water molecule, you know, they have hydrogen bonds in between, right? So if we maybe zoom in inside the water, the liquid water, the water particles will be actually having these hydrogen bonds. So here delta negative, delta positive, delta positive, delta negative, delta positive, delta positive. So you are having these hydrogens on bond between. So that means you have what is actually evaporating. So evaporating means one by one the molecules are entering the gas phase one by one. That means they don't have, they are fairly apart now. But if we think about liquid phase, they are somewhat closer. But if we think about the vapor phase, they are individual particles. So H2O molecule is one individual particle, one H2O molecule, right? So they have to be free from all the intermolecular forces. So they have to overcome all those interactions. So we have to actually break this hydrogen bond, then only this water molecule can escape. It's like maybe some of your friends are dragging you without going outside the class, right? So there are so many interactive forces inside the class. But if you are an isolated person, or you don't have any, or you don't have much intermolecular forces, you can easily go out of the class, right? It's the same scenario. You can think that way, right? So in order for the water molecule to escape from this liquid phase, we have to break this hydrogen bond. That means it requires more energy, isn't it? So we can say if the intermolecular forces are weak, those molecules will have a higher vapor pressure. So vapor pressure of this CH4 will be higher than the vapor pressure of water, the same condition. Why is that? Because they don't have any intermolecular forces inside, so they will easily evaporate. So their evaporation rate will be higher, so they will have a higher pressure. Pressure means, you know, the particles the force exerted by the particles on the wall. So when the number of particles are higher, that means the vapor pressure is high. So for the first point, so you should be able to understand all these. That means when the strength of the forces holding the molecules together is higher, their vapor pressure will be lower, right? Then how about the temperature? So let me draw another very simple two diagram. So we are considering water. Now the temperature is different. That means maybe a room temperature, and here we are heating such closed system, maybe to 80 degrees Celsius. Here the temperature. Here this is that just the room temperature. What happens when you heat? These particles inside, they will gain energy, they will gain kinetic energy, so that they will move fast. That means there is the more tendency for them to move to the surface, then they will evaporate more. So there will be more vapor pressure when the temperature is high, right? Here the vapor pressure will be high. So this is how we measure the saturated vapor pressure. This is the barometer setup. So you can see here we are having this mercury column. This first one is just in air, kept just in air, right? So here this is the vacuum we have, and then what we are doing, we have to add a few drops of the liquid, of which we have to measure the saturated vapor pressure. That is using a dropper, as you can see in the diagram, so that this liquid will enter to the top, and then they will start to evaporate, and kind of they will build that saturated vapor. So saturated vapor pressure. So how we are measuring, so you can see because of that pressure, you can think it like this. So initially the mercury column, it's empty, this is empty or vacuum. After we have this is mercury, this is the new liquid portion. So now they are vapor particles or vapor molecules, right? So they now exert a pressure on this surface. Because of that pressure, what happens, you can see this mercury column is coming down, right? Then we can see a difference between the original height of this mercury column and the current height, because the reduction of the height due to this vapor pressure. So that is called the saturated vapor pressure of that liquid that we are considering. That's how we measure this, right? Okay, so this is the variation of saturated vapor pressure with the temperature. So you can see it's increasing with the temperature. It's very clear because when the temperature increases, the particles, they get more kinetic energy. That means they move faster. So the particles having higher energy than the energy required to escape is getting high. Because of that, the vapor pressure is getting high. Okay, now let's see. In our day-to-day life, we say this is a volatile liquid or non-volatile liquid. So let's see the difference between these two liquids using the knowledge of saturated vapor pressure, right? So volatile liquid means they are highly volatile. That means they have relatively high vapor pressures. They are easily volatile. That means their particles will be evaporating very easily, so that they will have a higher vapor pressure, right? And non-volatile means they will have less vapor pressure. And volatile, yeah, as I already mentioned, they evaporate readily. Here this non-volatile, they evaporate very slowly. right? And then the substances with vapor pressures greater than that of what actually we are saying, referring as volatile, where the substances they are having greater vapor pressures than water. We are comparing with water and we are telling this character, right? And here this is lower than that of water. These are the examples, you know, actually from your day-to-day life. So here diethyl ether, acetone, gasoline, non-volatile, we can say plenty of things. So here these are very few examples. Okay, so the equilibrium vapor pressure or the saturated vapor pressure of a substance at a particular temperature is a characteristics of the material. That means it is, if we in a particular temperature, if we take for a particular material, that is a constant value. It's like boiling point or the melting point, right? Right, it does not depend on the amount of the liquid, right? For example, if we think about the boiling point, which is a very convenient example, you know, if we take even 2 liters or 5 liters or 100 liters of water, the boiling point is at 1 atm, it is 100 degrees Celsius, right? So it does not change with the amount we are taking. The saturated vapor pressure is a constant value. So this somehow depends on several factors. Actually, we discussed these factors in earlier, right? So what are those factors? Actually, we discussed 2 factors. If you can pause the video and think. Right. So it's actually temperature and intermolecular forces. So we actually discussed about this, how they affect. So here you can see the curve. This curve depicts actually the vapor pressure versus the temperature. Here there are several substances. Diethyl ether, first one is diethyl ether. I'm not sure whether you can see clearly. Then the second one is ethanol, third one is water, then an octane, ethylene glycol, and the mercury. So you can see there is an exponential increase with the temperature. So if we think about this increase of this vapor pressure compared to ideal gas, this increase of vapor pressure is fairly high, right? Because when we increase the temperature, actually the fraction increases exponentially, right? This exponential increase actually make the difference. Okay, so what is actually a boiling point, right? So if you think about a water container, you can see there are so many things going on, you know, inside. If you look at this diagram, right, so this is solid ice and water. So actually if we the summary is, if we go inside deep the container, there are lots of intermolecular forces or attractive forces, so it's hard for them to escape. So if they have to escape from the surface, we have to actually give energy to increase this vapor pressure. Actually boiling happens when the vapor pressure of this system is equal to the external pressure, right? Then that is where the boiling happens. Actually this bubbling and everything they happen due to this boiling. So what happens when the temperature of the liquid increases? That's where the vapor pressure build up, and when the vapor pressure is equal to the external pressure, the atmospheric pressure, we say it is boiling, right? So when it boils, you know, the bubbles bubbling starts, and you know the temperature at which liquid boils exactly at 100 kilopascal. That means 1 atm pressure is the normal boiling point we are talking about. That normal boiling point for water is 100 degrees Celsius, right? So this is actually a summary. You can see when the vapor pressure is equal to the external pressure, that is where the boiling happens. So this depends on actually elevation, depth in the liquid, whether you are in a vacuum, a pressure cooker, etc. Right? So this is just a glimpse. You can see boiling point of water at Everest. It's lower because the elevation is high, right? Now the pressure is lower, and when we go high at sea level, it's 100 degrees Celsius, and in Dead Sea we are going deep, so the pressure is high. That means the temperature or the boiling point is also high. So what's happening actually inside the pressure cooker? The steam builds up, the internal pressure is going up. That means the boiling point is also going up. So this everything happens in a very quick time. That is the benefit of the pressure cooker. So inside the pressure is increased than the atmospheric pressure, so thereby the increased boiling point, that is boiling point is increased, thereby they quickly they get boiled and cooked. So yeah, so that is actually the end of this video. I will meet you in our next video.